Hello, y'all, and welcome to Lesson 13, Structure 1.4.1. This is where we're going to start talking about counting particles by mass. We're going to be using the mole. So our guiding question is, how do we quantify matter on the atomic scale? Which is important because matter on the atomic scale is so small that dealing with one or two atoms just is not something that we can do in a lab, nor is it something that we can see or deal with. So in this lesson, we're covering the mole. It's the SI unit for the amount of substance. One mole contains exactly the number of elementary entities given by the Avogadro constant. We'll talk about that. And by the end of this, we should be able to convert the amount of substance N to the number of specified elementary quantities. And generally, N is used to refer to number of moles. So convert some number of moles to the number of entities. We'll talk about that too. So let's say what an entity is. It is an atom, a molecule, an ion, electron, or any other particle specified by a group of particles. So literally anything really small that we're going to be dealing with. And then the Avogadro constant is in the data booklet. It has the units, mole to the negative first power, so 1 over mole. And we'll talk about that too. So before we even really get started, we have to figure out how we quantify things. So generally we use words to quantify numbers, which sounds really weird because numbers are already numbers, but we do it all the time. So when you are putting on some pants, you might say you're putting on a pair of pants. So if we have two things, the word that means two things is a pair. So we use pair to mean two things. Let's say you're grabbing some eggs. You're getting 12 things. If you want to grab 12 things, instead of saying 12, you usually say a dozen, unless you're at a bakery, and then you say a baker's dozen, which is 13, not 12. Maybe let's say you are getting lumber and you want 144 pieces of lumber, so 144 things. We actually call that a gross. A gross is 144. Now, the main issue here is that whether we have two things or 12 things or even 144 things, if those things are really small, like atoms of uh, oxygen or atoms of carbon, we still can't see any of this. Heck, we don't have stuff detailed enough to pull 144 carbon atoms in a basic lab, chemistry lab. We can't just say, oh, I want 144 carbon atoms. Easy. Um, we need something that quantifies a larger number. So generally, when we're dealing with things in an atom, we're dealing with things on the scale of 6.02 times 10 to the 23rd things. And that we call a mole. So you can use it the same way you would use a pair, a dozen, or a gross. You can say, I want a mole of water. And that means you want 6.02 times 10 to the 23rd molecules of water. Just for a quick demo, that is this one, two, oh, whoops, sorry, I messed up. Two, three, four, five, six, seven, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. This is generally the scale that we get things when we're talking about atoms. This is how shockingly large that number is. So 6.02 times 10 to the 23rd is 6. Is this 602 sextillion things? So how do we actually use this? What do we do it for? Um, so the big thing here is that a mole, you'll notice I said I had no E, but I had an E there. It doesn't matter. Mole and mole are the same exact thing. But a mole specifically is a number. You need to keep that in mind. It's just like a pair, dozen, or a gross. It is just a word that means a number. It doesn't matter what you're dealing with. 1 mole of iron atoms will always be 6.02 times 10 to the 23rd atoms of iron. 1 mole of water molecules will always be 6.02 times 10 to the 23rd molecules of water, which I'm now going to say H2O. 1 mole of electrons will still be 6.02 times 10 to the 23rd electrons. If I said 1 dozen iron atoms, it would be 12 iron atoms. So we can just say mole, and it's the same thing every time. Heck, 1 mole of egg is 6.02 times 10 to the 23rd egg. So I hope this clarifies the point that mole is just a number. And so how do we actually use it? Well, when we're using it in math, we actually use what's called, use the Avogadro's constant. Now, real quickly, we call it Avogadro because that's the name of the guy who discovered the mole. It was a very long name, something Amadeus, something Avogadro. There's like 5 names, and I can't remember it. But Avogadro is the name of the guy who discovered the mole. So the number is also sometimes called Avogadro's number. But we use the Avogadro's constant, which is 6.02 times 10 to the 23rd uh, elementary particles mole inverse. So what that really means is 6.02 times 10 to the 23rd divided by mole. It's the same thing. So how do we actually use it? Well, the best way to do that is with some examples. So let's start with something simple. If we have 1 mole of carbon atoms, uh, let's spell it out, carbon atoms, we can say how many atoms is that? How many atoms is it actually? You might even say if we have 1 mole of carbon, you do not need to write the atoms. How many atoms? So we would start by writing our given like any math problem. 1 mole carbon. What we're then going to do is draw some big parentheses that have a top and bottom. And this is not how the textbook is going to say you do it, but I do it this way because this leads us into the idea of stoichiometry or dimensional analysis. But we're going to use some big parentheses. We are going to use Avogadro's constant. Now, I notice in Avogadro's constant, mole is on the bottom. And so I'll actually keep that. So I'll put mole on the bottom, which therefore means 6.02 times 10 to the 23rd. And my elementary particle, which we described earlier in the standard, is atoms on top. When I multiply these, because you should know from math that parentheses means multiplication. So when I multiply these, mole will cancel with mole, just like if you were doing a problem of x, or sorry, like A times B over A, A's would cancel. Well, that's the same thing that's happening here. Moles cancel out. So then it's just 1 times 6.02, which is equal to 6.02 times 10 to the 23rd. We still have atoms, so we're still going to write atoms. And we still have carbon, so we're going to write carbon. And that's our answer. So that's how we use the constant. Let's try it with another example. After I've written the problem, you can pause it and see if you can do it as well. So that was problem 1. Let's go to problem 2, and we're going to do 3 problems today. Let's say now we have 2 moles of iron, and I want to know how many atoms that is. You know what? We'll do 4 problems. I'm taking it back. So go ahead and pause it if you want to try it out. Otherwise, we're going to get going. So I start with 2 mole iron. Once again, I draw my big parentheses. I put mole on the bottom. And I put 6.02 times 10 to the 23rd atoms as my elementary particle on top. I will cancel the mole as they can cancel. And then I will recognize that 2 times 6.02 times 10 to the 23rd is about about 1.204 times 10 to the 24th, which I'm going to round this down to 1.2 times 10 to the 24th. atoms iron. All right. So that's our answer. We can actually go the other way. So we're going to do that in problem 3. We're going to go from 2.4 times 10 to the 24th. Um, we use a different elementary particle, molecules of water, and we're going to try and find out how many moles of H2O. So go ahead and pause it if you want to try it yourself. Otherwise, here we go. 2.04 times 10 to the 24th molecules of H2O. Now, before, I made sure that mole would cancel out with mole by putting it on the bottom. But now I don't want mole to cancel out. I actually want to end with it. And I want to end with it on top because this says mole, not mole to the -1. I want it on top. So I'm actually just going to go ahead and cheat a little and put mole on top. But what that means is I must put my number and elementary particles on the bottom. So I'm going to do that 6.02 times 10 to the 23rd molecules. And my molecules will cancel. And so I will have 2.04 times 10 to the 24th divided by my big number, 6.02 times 10 to the 23rd. And when I do that, I get an answer of about 4.0 times, actually, sorry, not 4.0 times anything, just 4.0 mole of water. It is more specific than that. It's going to be like 3.9. Ooh, you might be yelling at your screen because I messed up. It's 2.4, not 2.04. Anyways, it's 4.0 moles of water. All right, last problem. Problem 4. So I'm going to say how many atoms of oxygen in 3 moles of CO2. So this one's a little harder. When I look at CO2 and I notice that I have one carbon and 2 oxygens. So for every 1 mole of CO2, I actually have 2 mole of oxygen. So there's a couple ways I can do this. The first way is by recognizing instead of 3 moles of CO2, I actually have 6 moles of oxygen, and then I'm converting moles of oxygen into atoms. Or the alternative is I can convert 3 moles of CO2 into atoms, and then from atoms of CO2, or sorry, not atoms, molecules. And then from molecules, I can convert to oxygen. Now, I'm going to actually do it the first way because I find it a little bit easier. So I recognize that for 1 CO2, I have 2 oxygen. I'm going to actually just clear this up a little. So once again, I'm recognizing for 1 mole of CO2, I have 2 moles of oxygen. Therefore, for 3 moles of CO2, I have 6 moles of oxygen. So I'll go ahead and start with 6 mole oxygen. I want to cancel out mole, so I'll put mole on the bottom. 6.02 times 10 to the 23rd, my particle this time is atoms. And I will cancel mole with mole, and I will get a final answer of about 3.6 times 10 to the 24th atoms oxygen. And with that, we are done. Hopefully this helped you figure out moles a little bit more, and have a great day.